OK, so the final thing I want to talk about in terms of NRQCD is the NRQCD renormalization group. So the NRQCD renormalization group equations. And this is a kind of interesting topic that we're not going to cover in detail, but I'll give you an idea of what happens here. So let's first just think about the renormalization group. It's a running between scales. So what are the scales in the problem? Well, naively, we just have m, and then we have mv, and then we have mv squared. And this is much bigger than this is much bigger than that. So you would think that the way you would do the RG is you would match at this scale, run down to this scale, match at this scale, and then continue running down to this scale. That would be the very natural way of doing the renormalization group. And for some parts of the theory, you can actually get away with that. But it turns out that, very interestingly, in general, you can't. And the reason that, in general, you can't get away with this is because NRQCD actually couples together the energy and momentum scales. E is equal to p squared over 2m. And that means that the energy and the momenta are tied by the dispersion relation. So for example, if I put a cutoff on the energy, a hard cutoff on the energy that says it's less than some lambda, that still allows 3 momenta up to lambda times m, a larger scale. And so in general, the way that a cutoff on the energy translates to a cutoff on the momenta is through this dispersion relation. And that means they're tied together, these two scales here. OK, so this makes NRQCD a kind of interesting theory from the point of view of the renormalization group. The E and P are coupled. And so we can't just think about the renormalization group this way in general. So the trick that we can do to get around this is the following. It's what's called the subtraction velocity. So we're used to having subtraction scales, like mu from dimensional regularization in MS bar. But here we're going to convert to something that's a velocity. So the way that this works is we think about having a mu scale for soft physics, which we can write in terms of another thing which we call nu, and that's the subtraction velocity, is nu. And then for the ultrasoft, we do something similar, except here we have a mu that's going to be m nu squared. And now the tying together of these two scales is because I use a common nu for both parts of the problem. And the way that you should think about this is if I think about the soft or ultrasoft fields, there's a mu s to the epsilon, a g to the mu s when I have a soft field. And then there's a mu u to the epsilon, g of mu u, a u of mu when I have a gauge field, which is ultrasoft. OK? And so we're going to have both mu s's and mu u's in the theory, and then translate them into this nu through these formula. And that's the trick. So how do you figure out whether you have mu s's or mu u's? Well, you actually have everything you need in the theory to determine that. So really what you can do is if you're working in dimensional regularization, so your d is 4 minus 2 epsilon, you could just do the power counting, the v power counting, in d dimensions. And that will determine the power whether you need a UU or a US. And in these very simple examples, you say that the AS field here is of order MV, but in d dimensions it's 1 minus epsilon. So it's MV to the 1 minus epsilon. And then this US that has also something of order MV, where I choose my nu to be of order V from a power counting perspective. This compensates for the field, and likewise here. So they're sort of paired together by this power counting statement. OK, so that's how the theory deals with figuring out which one to use. And then it's very beautiful. It does exactly what you'd want. When you actually look at logs in this theory, because everything is homogeneous in the way EFT works, you're going to get logs. And if it's an energy log that you get, you'll get a mu u. And if it's a momentum log, you'll get a mu s. OK, so k is a momentum, e is an energy. You'll get these two different types of logarithms. There's also times in the theory where you can get something that has me. And me is like a momentum squared. And you could, for example, get a log like this, where the ME is showing up, but then it's compensated by mu s squared. So these are all logs that, if nu is of order v, are small logs. And the renormalization group is about introducing scales so that we can minimize logarithms and put the logarithms into renormalization group evolution factors. And that works the same way as usual in this EFT, except we're deriving renormalization group equations for this nu rather than for the mu's. So what we do when we think about running is we run in nu. So we start at nu equals 1, where all the scales are equal, and then run to nu equals some typical velocity. So v0 here is just some typical velocity of the system, some scale choice. And what that does in this picture here is simultaneously we go from m to mv and m to mv squared. So we're simultaneously doing this while at the same time doing this when we lower nu from nu equals 1. And then we reach these points when we get nu equals v0. OK, and so that's the way the subtraction velocity works. And what does this do for you? So we're not going to go through any examples, but what this does for you is it sums logs. That's what the renormalization group always is doing. And in this case, the type of logs that it sums are logs of the velocity. So you'd have alpha log v or alpha log v squared, depending on which of these type of combinations you have. And then those are raised to the k power. And you sum up infinite series like this. In cross sections, for example, that involve the bound states, or in decay rates, or in energy levels, various observables that you might calculate. OK, so that's typical. And it's kind of interesting to think about it in energies, because in the energies, you don't have any v anymore. The kinematics is fixing the energy. If you think about just the Coulomb bound state energy, if you talked about a bound state energy, it's just a function of alpha. But remember that v is of order alpha in this non-relativistic system. So actually in the bound states, for the bound state energy, we're actually summing logs of alpha, or we're determining logs of alpha. And the first type of log alpha like that you can encounter is actually one that shows up already in QED. And it shows up in the example of looking at the hydrogen Lamb shift. So in the hydrogen Lamb shift, there's a logarithm that shows up at order alpha to the 5th, log alpha. And that logarithm can be related to the renormalization group. OK, this renormalization group here. And you can determine logs of alpha in the fine structure of hydrogen and in the Lamb shift corrections in hydrogen and higher order corrections using the renormalization group. OK, so that gives you a taste for how the renormalization group works in NRQCD without going through any explicit examples. And it's a very interesting topic. And I've just given you a first look.